Hi, so we're back. As promised, we will move on to the Navier-Stokes equation in its traditional form. But before doing that, I figured we can make use of whatever we've learned so far, especially with regard to stream functions and vorticity and everything, to investigate a few interesting properties before moving on to the Navier-Stokes equation, which is in some sense one of the cornerstones of fluid dynamics, right? So let's first consider flows that are incompressible, in other words characterized by divergence of u equals 0. Remember the definition of incompressibility. An incompressible flow is one for which a Lagrangian observer, an observer sitting on top of a fluid parcel, does not discern any changes in density. It is very important to keep this in mind. An incompressible flow is one where the straight, this is equal to 0. In other words, the changes in density as discerned by a Lagrangian observer are 0, or equivalently, and this is usually what's normally referred to. This is the most popular definition for incompressible flows, and that's what we've got here. Okay, so that's what we've got here. And let's also consider flows that are irrotational. Okay, in other words, the vorticity, which is defined by the curl of u, is 0. In other words, and I will say that an irrotational flow is one which is inviscid. Why? Well, let's look at it. I said irrotational flows where the vorticity is equal to 0. Now we've already discussed this, but it's useful to recap it. Let's consider a situation where you have a viscous flow, the same diagram that we've sketched many times before. Here's the sort of bottom layer, and here is the free surface of the fluid. Consider flow of a viscous fluid such as honey. Again, you have x and y, so this would be u of x. So a situation where you have a gradient of the u of x as you proceed in y. In other words, a flow of a viscous liquid such as honey, where the top layer is moving fast, the next bottom layer is moving a little slower, the next bottom layer is moving a little slower, so on and so forth. Okay, this would be one where if you placed a little paddle wheel in here, it would rotate because the force here on top is slightly larger than the force here, so it would rotate. Okay, and this follows. So this is a situation where dux. So this is a situation where curl of u is not 0. Okay, you can arrive at this also by looking at the definition of curl you remember how a curl is written. Like this, and ux, uy, uz. This is how. So only when you have these cross terms, d over dx of uy or d over dy of ux, like so. Okay, only when these cross terms are non-zero, you have a curl that's non-zero. If that is not so, then the flow is irrotational and this paddle wheel will not rotate. And what is the situation where the paddle wheel will not rotate? It's one, well, where the flow is irrotational, or there is really no gradient, there is really no sticking between the layers, and the flow is effectively inviscid. Okay, so let's consider situations where both of these are true. A flow that's incompressible and also irrotational. This is not just for mathematical convenience. Well, part of it is really. There are many elegant solutions that can be derived using these two conditions, but it's also something that's of great practical importance in many situations. Okay, so let's consider a situation where both of these are satisfied. Now, by virtue of irrotationality, by virtue of the fact that the curl of u is 0, you can define a scalar potential like so. Why? Because the curl of the gradient of a scalar function is always 0, right? The curl of u is 0, we already said that. We already said that. In other words, the curl of the gradient of phi is equal to 0. In other words, by virtue of irrotationality, we can define a velocity potential, right? So, this has to do with inviscid flows, as we will see later. I just explained this to you. By virtue of incompressibility, right? So, we've already said that u is defined as a gradient of a scalar potential. On top of it, we are saying that the flow is incompressible. In other words, the divergence of the gradient, which boils down to this Laplacian here, is equal to 0, right? So, we are looking at solutions of Laplace's equation for the velocity potential. Okay. And this is something that's well known from many fields, say from electrostatics. So, we can take advantage of many of these results in dealing with flows that are effectively incompressible and irrotational. Okay. So, remember that this is a consequence of both these. Okay. Only if both of these are satisfied, you can have you can have a potential. You can solve Laplace's equation to get the potential, and from the potential you can get the velocity field. And we can, like we said, we can use solutions that are familiar to us from electrostatics. Recall, the scalar potential has to be featureless. I simply say recall, and this is from, let me see what I've got on my, so before saying that, let's explain this statement a little bit. So, what are we talking about? We are talking about right, or well, this came from the fact, this simply came from the fact that that's what this is. Now, I made the statement that this implies that phi is featureless. By that I mean this is the phi does not have hills or valleys or anything, it is a nice flat surface. You either know this from electrostatics or you remember it, or even if not, we can. So, this is essentially Laplace's equation. So, any solution to Laplace's equation is featureless. One way of understanding this is by discretizing this, right. How, say in just one dimension you discretize this second derivative, right. How does it look like? It looks like something like phi I minus 1 minus 2 plus over either 2 delta x or delta x. That is what this one is, the discretized version of that. Okay, so this is a phi I plus 1. What this is really saying, and you can verify this. Okay, you discretize a double derivative just in one dimension, and that's what this is. What this is really saying is that the middle point phi I, so that you're discretizing on a grid like this. Yeah, this is I minus 1, and this is I plus 1. And you can discretize in the other direction also, but it's not so important for the purposes. So what you're really saying is that the middle point is really the average of the value of phi at point I is really the average, yeah, and this, if this is equal to 0, that means the numerator has to be equal to 0, right? So what you're saying is that phi I is really the average of this and that. So you're really averaging. If there are hills or valleys, yeah, you're averaging really removes features. If you think about it, if there's a peak here and a valley here, if there's a peak here and a valley here, what this process is really doing is averaging over the peak and the valley and getting an average value at the middle, and you keep doing this. Okay, so in doing so, you ensure that the solution to this equation is featureless. In doing so, you ensure that this is feature. This is one way of understanding this. There are other ways of understanding this also. Okay, so I figured I would point this out before moving forward because this is such an important point. The other thing to remember is that by virtue of incompressibility, by virtue of this condition, yeah, you can define a scalar stream function psi. Well, it's for 2D velocity fields at any rate, and recall streamlines are lines along which the stream function, this is conserved, right? You can write down by virtue of incompressibility, by virtue of the fact that the divergence of u is always equal to 0, that is the assumption we are making. So, the divergence of a curl is equal to 0, we know that. So, you can write down stream function like so. And so, since psi is 2-dimensional, the direction is along the z hat direction. So, you can write down this kind of a equation for u, and this effectively the stream function by virtue of its name, and we also saw how a stream, there are different definitions of a streamline. The physically, intuitively appealing definition of a streamline is one where you are essentially just joining the little velocity vectors like that. You join them together and you form a streamline. Yeah, and you can also write it as like that. You can also write a streamline streamline is one where the stream function psi is conserved. In other words, each streamline has a particular value for psi. Psi labels a streamline. Okay, right. So that's a stream function, and taken together, in other words, this equation and this equation taken together gives you this condition, and I urge you to work this out, and we will show why this is so also a little later on. Taken together, this implies that equipotential lines and streamlines are orthogonal. Okay, so the gradient of the equipotential surface and the gradient of the stream function surface, you dot this together, and they're equal to dot product is equal to 0. So that's just what this is saying. Okay, and this is also something that's familiar to you from electrostatics, right? You move from equipotential surface to equipotential surface, and that's the direction of the inelectric field line. Okay, so if you want to jump from one equipotential surface to another one, you are moving orthogonal to the equipotential lines, right? So that's what this is saying. There's also something that's familiar to you from electrostatics, right? So, and we hinted at this early on. You can apply the theory of complex variables to let's go on and we'll see why that is. Okay, so for two-dimensional flows from incompressibility. Remember, we are talking about an incompressible irrotational fluid, incompressible inviscid fluid. Yeah, so if you want to restrict yourself just to two-dimensional flows, this is essentially the same as this, right? It's simply the definition, and this can be related to the stream function as this, right? That simply follows from this. This simply follows from the definition of the stream function, just follows from the definition of stream function here. Okay, you only have ux and uy, and therefore from this definition you just take the curl and this follows. This follows. Okay, this is from incompressibility. From irrotationality you get this. Okay, ux, in other words, from the fact that from irrotationality is just a statement of messing up here. Right? You merely write down, irrotationality is simply saying that curl of u is equal to 0, and you remember the curl is just I. We had written this down already. No need. Yeah. So this definition here, right? So you don't have to take this last column because you're only talking about two-dimensional flows. So if you just consider this much, this follows, right? So therefore, you look at this and this. Taken together, taking both of these together, you get, d phi dx is d psi dy, whereas d phi dy is minus d psi dx, right? So this is very familiar. I mean, it's essentially the same as the Cauchy-Riemann condition for complex variables. It's almost as if, phi and psi form phi and psi taken together form one complex variable. Okay, and this is the Cauchy-Riemann condition for complex variables, right? So I just wanted to point this out, and this is as though ux and ui are components of a single complex variable. One can therefore apply powerful techniques from complex analysis to solve for the flow field, two-dimensional flow fields. I must emphasize. Although a lot of this is done for mathematical convenience, it's also very relevant to real flows. These are the early days. This is how much of the early progress in fluid mechanics was made. And you can also easily verify. You remember we remarked on this condition, the fact that streamlines and potential lines are orthogonal to each other. This follows directly from the Cauchy-Riemann condition. Okay. You can also, in addition to the fact that del squared phi equals 0, which follows from incompressibility and irrotationality both. Okay, you can also show that del squared psi is also equal to 0. So both are solutions to the Laplace equation with different boundary conditions, of course. Okay, but both are solutions to the Laplace equation. So this is another remarkable, So both the stream functions and psi and the velocity potential phi, both are solutions to the Laplace equation. In practice, and this is the trick, in practice though, one usually identifies an already known solution to the Laplace equation and then hunts for a physical situation where it's applicable. Turns out that there are very many, it's not simply playing games with mathematics, there are very many physically interesting situations where such solutions are applicable. Let's look at one or two of them. Right. So an example of inviscid, incompressible, irrotational flow around a smooth sphere. These might seem like lots of adjectives: inviscid, incompressible, irrotational, smooth sphere, but it's a highly idealized situation to be sure, but it's very, very, you look at these ideal solutions and you have a fairly good idea of how a real world solution will behave. Okay, so this lot of value to looking at these idealized solutions and figuring out the general behavior. I'll leave it at that. Right. So now, from mathematics, the general solution for del square phi, and remember phi is the velocity potential in 2D polar coordinates. 2D polar coordinates, as you know, r and theta. Yeah, like so. Are just, this r and theta. These are the only two things that matter. This is the general solution. I'm simply writing this down. You can find this in many places. You can think of this as it simply follows from the definition of del square in 2D polar coordinates. You can this follows from Legendre polynomials. It's really a Legendre polynomial. That's what it is. These are YLMs, and so you can see only two variables here. You can see the r, and you can see the theta. Right. So there are only two variables here. So this is the general solution, and you apply the boundary conditions appropriate to an inviscid, incompressible, irrotational flow around a smooth sphere. You apply the appropriate boundary condition and you get the solution immediately. We will see how. Okay, we won't go through the gory details, but we will see how. Yeah. So you see, for a smooth sphere of radius a, the boundary conditions are d phi. I claim that these are the boundary conditions. D phi dr equals 0 at r equals a. In other words, at the, so I claim that this is a sphere of radius a, and at the surface I am claiming that right. What does this mean? In other words, you remember from the definition of phi, and what was the definition of phi? We'll go back. We might have to go back a little ways. This is how phi was defined, remember? U is a gradient of phi. So if d over dr of phi is equal to 0, that means you're talking about the normal component of the velocity. But the normal component, this component, either you're really talking about the normal component of the velocity. So the normal component of the velocity is equal to 0. This is what we're saying with this statement. But the tangential velocity need not be equal to 0. In other words, you are allowing for infinite slip at the surface of the sphere. Okay, and this has to do with this adjective. Okay, so this adjective has to do with this. How do you think the boundary condition at the sphere's surface would look like for a viscous fluid? Think about it. An inviscid fluid is one where there is no sticking. The fluid does not stick to the surface. That's how you think about, think of the flow, for instance, a flow of honey past a solid sphere as opposed to the flow of a less viscous fluid such as water past smooth sphere, right? Water tends to slip more easily at the surface, whereas honey tends to stick. So tangential slip is allowed for an inviscid fluid, not allowed for a viscous fluid. Okay, so at any rate, we are now talking about inviscid fluids. So this is the first boundary condition we apply, and you see this is the second order. It's like a d square over dx square or d square over dy square kind of situation. So you need two boundary conditions, right? So this is one boundary condition already. The other boundary condition, the other natural boundary condition is, now I'm mixing up between polar coordinates and rectangular coordinates, but really it's a small thing to transform between two-dimensional polar coordinates and xy coordinates. What this means, what this condition means is that at very large distances from the sphere, say like so, you have a sphere and this is x and this is y. Although we are really talking in terms of spherical polar coordinates, we're talking in terms of r and theta. What we're really saying is at infinity, okay, very far away from the sphere here or here, let's just draw it here. Okay, the sphere hardly has any, the fact that there's a sphere present hardly has any influence on the flow. Okay, if the flow was flowing in the x direction, like so, no question of any gradients or anything because we are talking about inviscid fluids. So, the sphere hardly disturbs the flow, okay, very far from the surface of the sphere. So, we have two kinds of boundary conditions, one very far from the surface of the sphere, one at the surface of the sphere. At the surface of the sphere we have this boundary condition, very far from the surface of the sphere we have this boundary condition. In other words, we are saying that very far from the surface of the sphere the velocity is entirely in the x direction with some amplitude u. So, these are the two boundary conditions. When you impose these two boundary conditions, this and this, on this general solution, yeah, okay, so here's the other thing. So, either you think in terms of the velocity, or you can we are really looking at the potential, aren't we? So, it's useful to write down the potential, and that turns out to be u r cosine theta, and this is nicely written down in spherical polar coordinates. And so you have these two boundary conditions, this and this, on phi. So, this would be I think that's called the Neumann boundary condition. This is called a Dirichlet boundary condition, unless I've got them mixed up. At any rate, this is a mixed. You either have two Dirichlet, two Neumann, or a mixed. Here is a boundary condition on the variable itself, and here is a boundary condition on the derivative of the variable, normal derivative to be specific. Both of these you apply those to this particular solution. Yeah, so that's what this means, like I explained a moment ago, and the particular solution is this. Okay, this incorporates both the boundary conditions mentioned earlier, and you having gotten the potential, it's a simple matter to just take its gradient. You would have to take the gradient in spherical polar coordinates, obviously, and that's what it looks like. Okay. This is what the solution looks like. This is the solution to the flow of an inviscid irrotational fluid, the same thing really, inviscid incompressible fluid around a smooth sphere. There you go, right? And what does it look like? That's what it looks like. You plot this as a function of r and theta, and that's what the streamlines look like. Okay, and this is the actual photograph of streamlines. So you actually inject a dye through a sphere, through a flow that's flowing smoothly past a sphere, and that's what it looks like. These are the non-ideal, these are the kinds of this broadening, these are the kinds of things that will not be captured with this nice elegant solution. But you can see how closely it resembles the actual situation. So, this is an example of a situation where where these idealized solutions are very useful. Okay, right. So that's what this is where I'll stop for the time being, and we will go on and investigate a few other interesting consequences of the potential function and the stream function, and before moving on to the Navier-Stokes equation. Thank you.